Good morning and welcome to this latest edition in the Elephant Conversations. And today it's my pleasure to welcome my friend Charles Mutiso. Charles has a background in math and physics and did his research in the near Earth space environment. Later, if we have time, he can tell us a bit about what that exactly means. And now, Charles mostly writes software, and he's also a stock market advisor. But welcome, Charles.
Thank you very much, John.
Charles, the reason we're having this conversation today is because there's been lots of conversations in Kenya about blockchain, Bitcoin, and other cryptocurrencies, etc. And I wanted you to take us and our viewers through, what does blockchain mean, and then what is Bitcoin and other cryptocurrencies. Just take us through it very simply. If I was just to ask this very basic question, everyone's talking about this technology of blockchain that was invented by a gentleman called Satoshi Nakamoto, who disappeared, who no one can find. But perhaps you can tell us a bit more. Let me just, what is blockchain, Charles, and why is it spoken of as being so revolutionary in terms of, it's almost like a quantum leap in technology? People talk of it in terms of, it's like another revolution technologically for us.
Right.
Fire
Thank
away.
you. Thank you, John, so much for having me. Glad to be here and to share what I know about blockchain and Bitcoin. And I think the first thing I would say is these are two very different technologies. Blockchain and Bitcoin are two different things. So when people speak about blockchain, they may or may not be speaking about Bitcoin. And when they speak about Bitcoin, they may or may not be speaking about blockchain. Bitcoin technology is based on blockchains, but blockchains by themselves have very many applications not related to Bitcoin or other cryptocurrencies. And to understand the difference, I think we have to understand that there's a hierarchy of technologies and a hierarchy of elements that coming together build up into Bitcoin. So really what I'd like to do is to share or to explain some of these technologies, which when you put them all together, we end up with Bitcoin.
Okay. Fire away.
We'll start with what we call a hash. And I put together this small demonstration, which will hopefully help us understand some of these elements that, like I said, when you put them together, end up with blockchain technology and Bitcoin technology. So a hash is simply an algorithm which maps digital data to its own unique fingerprint. And the analogy is human fingerprints. Everyone has a set of unique fingerprints which can identify a person. Well, the analogy in the digital world is this hash, which is a fingerprint of any digital data. So you can think of any digital data, whether it's a file or some text or a movie or a hard drive. If it's digital, you can hash it and you can come up with this fingerprint. This at the bottom, this string starting with E3B0, that's the hash. That's the hash of this empty data set.
Okay. And the hash is generated by the algorithm and is totally unique to the digital information.
Exactly.
The digital data up there.
Exactly.
All right.
this is a hash of empty data, but immediately I put any data in here, the hash will change. So for example, if I just type a letter, Y, so the hash of the digital data Y is this string. This string, the hash, uniquely identifies this digital data.
What if you put in the digital data Kenya?
I can do that.
Okay, I can see it changing every time you
can see
every time you add a letter or any other bit of information, the hash is changing. Okay.
Yes, if I do something as small as add a full stop, this hash beginning with 74E1, if I add a full stop, the hash changes completely.
Okay.
I can make a change which may not be visible to the human eye. I can add a space and the hash will change. Okay. So any change whatsoever to any digital data will change the hash, which is the digital fingerprint of the data. So again, a hash is simply a string or a digital fingerprint which uniquely identifies a piece of data.
Okay.
It's important, there are a couple important things to note about this hash function. One of them is that the same digital data will always yield the same fingerprint. So again, let me cut this word Kenya. And remember the hash 74E1. If I remove it, I get back the empty hash starting with E3B. But if I paste in Kenya again, I should get the hash 74E1. Yeah. Okay. So the same digital data anywhere in the world run by any person, as long as we agree on the hash algorithm, it doesn't matter where you are or what computer you're running the hash function on, as long as the digital data is the same, it will always yield the same hash.
Just a pause. You say the hash is generated by an underlying algorithm.
Correct.
And maybe you're going to come to this later. What is that algorithm that is pervasive and that is available globally in a way that if I type in the digital data Kenya, it will produce the same hash every time?
There are many different hash functions. There are many different hash functions. This particular one I'm running is called, I'll type it in there, SHA-256. But there are many different hash functions. As long as we agree, you and I agree on what hash function we're running, if we agree we're running SHA-256, then the hash of SHA-256 run through that SHA-256 function will always be B3AB, whatever. Okay, so that's the first property, that the hash function always returns the same hash for the same digital data. The second very important quality of a hash function is that the hash is unique. There's no other set of digital data which can give me the hash E3B0 other than the empty data set.
Okay.
If I type in Kenya back, there's no other digital data possible that will give me the hash 74E18 blah, blah, blah. So it is unique in the sense that only this word Kenya can give me this hash. There's no other set of digital data in the world which will give me the same hash. So hashes are unique. And maybe the last important quality about hashes we've already mentioned briefly is that any change to any of the data will immediately change the hash. If I take out the A, the hash changes. If I change the last letter, the hash changes. If I capitalize the A, instead of 78, we have 111.
Okay.
Yeah.
All right.
So that's the hash function.
Okay.
Do you have any questions up until there?
No, I get it. I mean, it's a question I was going to ask. What if, you've capitalized the K. What if it's a small K? But clearly, it's not as if it's the algorithm is reading the data. It's simply interpreting it using the algorithm. So it's not reading it. So it doesn't understand Kenya with a small K and Kenya with a capital K as the same thing.
It doesn't.
No,
because to a computer, those are two very different sets of data.
Correct.
Yeah. Okay. That's the hash. Again, important point to remember is no matter how small a change you make to the digital data, we will get a new hash. So the hash is the digital fingerprint, which uniquely identifies a set of data.
Great.
We'll move on to the second set of
in the hierarchy
technologies. So we talked about this, and I showed you a sample hash.
Yeah.
Some useful properties of a hash is that you can immediately detect any change in the original data.
Yeah.
The hash of the original data and the hash of the tampered data will always be different. And a hash function is not so much concerned with ensuring secrecy of data. So it's not a mechanism which you can use to make data secret. It's a mechanism that you use to ensure that data has not been tampered with.
Okay.
Yeah, the data can be out in the open. The data can be public.
Okay.
But the hash ensures that data has not been tampered with. One example that you could use something like a hash function for is, let's say I want to write my will. I want to write my last will and testament.
Yes.
If I do this in an electronic form, what I can do is I can hash the will. Yes. The hash function works on any digital data. So I can make a digital copy of my will, say a PDF.
Yes.
And I can hash my will. And then I can give my heirs just the hash itself, okay. Just this string, the yes. E3B, I can yes. give them, I don't need to show them the contents of the will.
Yes.
I can just show them, I can give them the hash.
Okay.
And so when I die,
yes.
and my will is being opened, they can verify the integrity, or they can verify that this is the actual will simply by taking that digital document, running the hash function on it, and comparing the hash that they get out with the hash that I gave them previously.
Correct.
Because if any part of the will has been tampered with, if it's a fake will, if it's if anything in the will has been changed, then the hash function, the hash that comes out of the tampered will be different Correct. Than the hash of the original will.
Correct.
Yeah.
Okay. Okay. I see the tamper-proof quality.
Okay. That's important because, again, we're building up to the blockchain. So let's move on to this concept called a block. Okay, we're starting to get into blockchain. So now we're going to talk about a block.
Yeah.
There's certain concepts which I have to introduce for us to understand what a block is. One of them is this nonce.
Yeah.
There's a technical term for this number once. Yeah. Or a nonce. Yeah. Just think of it as a secret or random number. Just any number, yeah. Secret or random number. A block, for the purposes of this explanation, we'll say a block is data plus a nonce. Okay. This data can be any digital data. Okay. When you combine it with a nonce, we have what's called a block. Okay. Again, for the purposes of this demonstration, we'll say a valid block. Okay, we'll have valid blocks and invalid blocks. Yes. But a valid block will be when the hash starts with 4 zeros.
Okay. Okay. Why 4 and not 2 or 6?
Because we chose it. We have the capacity to choose what we want a valid block to be.
Okay.
It's completely arbitrary. It's up to me,
Okay.
or it's up to us to choose what we want the hash, what we want a valid block to be.
Okay.
But I can talk about this more a bit later.
Yeah.
And let me introduce this concept called mining. We hear it all the time in the cryptocurrency world, mining.
Correct.
You know, I'm mining Bitcoins, I'm mining Ethereum.
Yes.
So again, for the purposes of this demo, we'll say mining is when we find the nonce which makes a block valid. When we find the secret number,
yeah,
which when you combine it with a block, we end up with, I mean, when you combine it with data, we end up with a valid block. Okay. I know these are best explained using a demonstration. So I have a demonstration block here.
Okay. All right.
Let's go over those concepts again. This is just the block number 1.
Yep.
Later on, we'll build a chain and add more blocks. We have the nonce, the secret number.
Okay.
Here it is 72,608.
Okay.
We have some data.
Okay.
Even though you can't see this data to a computer, this is data. It's empty data.
Yeah.
Yeah. And we have the hash. This hash is the digital fingerprint of this data. Correct. Plus the nonce.
Okay.
Right?
Yeah.
Remember this, when we were on this page, we just had the data and we had a hash E3B0.
Correct.
But now in the block, we're taking the hash of the data and the block. I mean, the hash of the data and the nonce.
Okay.
Right?
Okay.
So when I take the hash of the empty data set and the hash of the nonce combined,
they produce a different hash.
They produce a different hash, which starts with 4 zeros. And so according to our arbitrary condition, which is a valid block starts with 4 zeros,
yes,
this is a valid block.
Okay, I'm with you.
You're with me?
I'm with you. I'm with you.
Up to here.
I'm with you.
Okay.
And the nonce is also, as you said, is also generated by an algorithm.
I'll answer that later.
Okay.
The important thing, the first important thing to note is if I change either the data or the nonce, I will change the hash and possibly invalidate the block.
Okay.
So for now, a green background indicates a valid block. If the background changes to be red, okay, it will mean the block is invalid. So let me make a small change to the data. Let me add a space. You probably won't even see that. I've added a space to the data.
Okay.
You can see now when I hash the data and the nonce has stayed the same.
Yeah.
But when I hash the combination of the two, the hash comes out as E84. And according to our criteria, which is 4 leading zeros, yeah, this is now an invalid block. Okay. Let me remove the space.
And we are back to the validity of the block.
Exactly.
We have the 4 zeros in the hash.
Yes.
The same nonce, the same block number.
Yes.
Okay.
If I add, let me make a change we can see. Let me add a full stop. I hash in the background, the hash algorithm is running. It has hashed the nonce and the data. It has come up with a hash D495. And again, according to our arbitrary criteria for what is a valid block, this no longer qualifies as a valid block.
Okay.
I can make a change to the nonce, right? This number, let me write it down, 72608.
Okay.
I can change the nonce and enter any arbitrary number. 1, invalid block. 2, invalid block. 3, invalid block. 4, invalid block. You know, I can enter any number I can think of and try to get a valid block.
Doesn't work.
Right?
Yeah.
It doesn't work because there's only one combination of this set of digital data.
Yes.
And the nonce, which will give me
a valid block.
A valid block, and that's 72608.
Okay.
Is this
No,
good up to here?
I'm with you up. I'm with you up to here. I've now understood what a block is.
Okay,
Even though this is a block, it's a valid block with no data in it, but
with no data.
any data could be there. It could be a PDF, it could be a photograph, it could any digital data can
Any
be
digital data.
could be a share certificate, it could be a driving license,
It could be a will.
a will, any kind of digital data can be put into that section. And
Right.
yeah, I'm with you.
Okay.
So we have one block now.
We have one block. So for this data, let me point out a few things. Or for this block, there's only one combination of data and nonce that validates the block.
Okay.
Let me use elephant.
Okay.
We have some data.
Yes.
We want to make this a valid block.
Yes.
Because we can't change the data,
Yes.
we can change the nonce, or we can find the nonce or the secret number, which hashed together with the data will give us
a valid block.
A valid block.
How do we do
that? Before we answer the question how, let me define what mining is, because that's exactly what mining is. Mining in cryptocurrency terms is when you find the nonce, which when coupled with the data gives you a valid block.
Hash. Okay.
Yeah, sorry. Yeah, a valid hash or a valid block.
Okay.
And so I'm going to press this button, mine, and my computer will start mining, or will start the process of finding the nonce, which together with the word elephant gives us a valid hash. So let me run the magic and press mine. So my computer is mining.
And using SHA-256, that algorithm, anywhere in the world, regardless of who you are, whatever you're doing, if you are seeking the valid hash, create a valid block for the digital information, the elephant.
Right, elephant.
This is the nonce that you're gonna get, whether you're in Alaska or in Lagos, Nairobi, Mombasa.
You could be in space.
So when you mine, this is the nonce you're gonna get.
Yes, as long as we agree on the algorithm. You know, we've agreed we're running SHA-256 to generate our hashes. Remember, one property of the hash function is it always yields the same hash for the same digital data. So you're correct. Wherever you are in the world, when your computer mines or tries to find the nonce, we will all end up with the same value of the nonce.
Quick question, just taking you back a little bit about SHA-256. Why did you choose SHA-256? I've read about it. I mean, is it the original algorithm? I know there are many others. What's it about SHA-256 as an algorithm in generating the blocks and the blockchains?
There has to be a balance between security, or I think privacy would be not privacy, security would be the number one consideration. But having said that, there are algorithms that are more secure than SHA-256, but there has to be a balance between several factors, one of which is security, the other is complexity or ease, or how fast can a computer generate the hash, because there are more secure hash functions like SHA-512, but it takes longer to generate the hash. For now, SHA-256 is adopted globally as the standard. But there are cases where SHA-256 has been proven to be insecure for certain applications. But for what we're doing, the internet, blockchain, SHA-256 is the standard. Before SHA-256, there was a standard called SHA-1.
Yeah.
And what happens, John, is as time goes on and as computers become faster and faster, they can break the hash function or the encryption function.
Okay.
So pretty soon we will move from SHA-256 and find some more secure hash function, simply because computers have become fast enough and can break SHA-256.
Okay. Yeah. I get you. Great. And so now we have a valid block for.
Now we have mined. We have mined the block.
Okay. We've mined the block.
We've mined the block. And by that, I mean, we have found the combination of the nonce and the data, which again, according to our arbitrary criterion, which is 4 leading zeros, we have validated this block.
Great.
Now, the reason we use computers to mine is because they're fast.
Okay.
I could sit here, John, and I could do 1 and, invalid block. I could go to 2, invalid. I could go to 3, and I could, I forgot the nonce, but let's mine it again. The reason we use computers is because they're much faster. So what this software running in the background actually did, it did exactly what I was doing, 1, 2, 3, but it did it much faster.
And that's why, okay, when one hears of mining for cryptocurrencies like Bitcoin, you have entire warehouses full of computers that need special cooling, simply because there are billions of transactions.
No, well, yes and no. You do have warehouses of computers, although nowadays it's actually acres. You have acres of computers, so it's not just a warehouse. You have several acres of computers, and they're doing exactly what we're doing. They enter a 1, and they check the validity. They enter a 2, but in Bitcoin, and we can talk about this more in depth later. In Bitcoin, the hash or the valid block is more, it's harder to find a valid block.
Yeah.
So the Bitcoin software automatically regulates the difficulty. So instead of 4 zeros, you could say, let's have 8 zeros.
Yeah.
So then your nonces would not be like 64,000. There'd be, 2 billion, or 20 billion, it would be a very large number.
Yes.
Which would take, that's why you need the specialized hardware. It would take much longer to find a valid block.
Understood.
Yeah.
Understood. So now we have a valid block.
Now we have a valid block. Just going back to some of the concepts from the hash, if I change any of the data, or if I change the nonce, I will immediately invalidate the entire block.
Correct.
If I add a full stop to the word elephant, and then in the background, I've run the hash of this data and the nonce.
Yes.
This is now an invalid block because the hash no longer begins with 4 zeros.
All right.
If I change the data, let me add a 1.
Okay.
I've invalidated the block.
Yes.
If I remove a 3, I've invalidated the block. There is only one combination of the nonce and the data. This particular data, which satisfies this our arbitrary condition for 4 leading zeros. Okay. It's actually technically that's not completely true, John, because there could be another nonce which gives me a hash starting with 4 zeros, but a different letters after the 4 zeros.
Correct.
But for this simplistic explanation, let's just say that there is one combination of the nonce and the data which yields this hash beginning with 4 zeros.
Okay, understood.
Okay. Great, we're doing good. So the key concepts, the nonce, the block, a valid block is when the hash starts with 4 zeros, and mining is when we find the nonce, which makes a block valid.
Correct.
Now let's go to blockchain.
Yeah.
The simple definition of blockchain is a chain of blocks.
Yes.
It is also a tamper-proof, immutable record of data. So tamper-proof in the sense that you can tamper with it, but it will immediately be recognizable that you have tampered with the data.
Okay.
So it's not tamper-proof in the sense that you can't tamper with it. You can tamper with it.
Yes.
But immediately you tamper with it, you invalidate the block, and it will be immediately noticed that you have tampered with the data.
Okay.
It's immutable. That same property of tamper-proofness makes it immutable.
Okay.
You cannot change the data without everyone knowing that you changed the data. And then any change in any of the blocks immediately invalidates the entire chain.
All right.
Once again, let me demo this.
Okay. So now this is now
This is now a blockchain.
A blockchain now.
Yeah. It's simply a chain of blocks. We've taken block number 1. We have block number 2. We have block number 3. We could go on and on. For here, I have 5, but we can just focus on the first 2 or 3.
Yes.
And this is similar to the previous discussion of the blocks, but now I've added just one more element here. This previous means the hash from the previous block.
Okay. Yeah.
Since this is what's called the genesis block, or the first block, we just arbitrarily give it the hash 000. But if you look at block number 2, you can see that the output hash from block number 1 is fed into block number 2.
Correct.
Where it says previous.
Correct.
And the output hash from block number 2, 00012FA is fed into. Yeah.
Excellent.
Now, what we're going to do, or what we've already done, is we have hashed the nonce, the data, and the previous hash.
Okay.
So this now becomes the data fed into the hash function. It's the nonce, the data, and the previous hash. We take the hash of all of that data, and we end up with a new hash.
Okay.
Starting with 00015. Okay.
Yes.
So again, let me just repeat that. We've taken the hash of the empty data set.
Yes.
The nonce. This has already been pre-mined. We found the nonce.
Yes.
Then we've taken the previous, or the arbitrary genesis block hash. We've taken the hash of all of them, and we've ended up with 0015. So this is a valid block.
Yeah.
Okay.
Yeah.
Then I take this hash output 00015, I feed it in here, and I take the hash of the empty data set, this previous hash, and the nonce, and I come up with this hash 00012FA96 etc.
Okay.
So let me demonstrate some interesting properties about the blockchain.
And then if you so some properties and also applicabilities. Yeah, because now, okay, now I've understood the block. Okay, I can now see the chain and how it works. Basically, it's the same principle as a block, but it's got this progression.
Exactly.
But how can this be used, for example, in financial to secure or to expedite? How can this be used in terms of financial transactions and other transactions?
Okay, I'll get to that. Let me demonstrate some properties first.
Okay.
If I add any data to the data block, what's going to happen to this hash?
It will be invalidated.
It will be invalidated. Then I'll take this invalid hash and feed it in here and hash all this. And what will happen to my hash here?
I think the entire chain is invalid.
Exactly. Yeah. So let me demonstrate. Let me add a full stop here.
All invalid.
And it's instantaneous.
Okay.
Okay. There's no time delay. Okay. In human terms, it's in computer terms, maybe there's a delay, but in human terms, there is no delay. Because as soon as I add a full stop, like you said correctly, this is now a new hash.
Yes.
140. It does not begin with 4 zeros.
No.
And then because this hash is fed into the second block, when I take the hash of this previous hash, the empty data set, and the nonce, I now have a hash which does not begin with 4 zeros. So this block is invalid.
Right.
I take this previous hash, I feed it, the 07FA, I feed it into the following block. I run a hash on the previous hash, the data and the nonce. I end up with something not starting with 4 zeros. And you can see the progression is the entire chain
has been invalidated.
Is invalidated just by altering something very small in the data.
Yeah.
If I go back to the original data set, we have a valid chain.
Okay.
If I change the nonce, what's this? 11316. If I change this in any way, same thing.
The entire chain collapses.
Yeah. The entire chain collapses. I can sit here all day trying to enter numbers to validate the block, and it will never be valid because the nonce or the number once can only be used once to validate this block, and since it's a chain, validate the entire chain.
Okay.
It doesn't have to be the first block. I can mess with this, the second block, right? If I mess with the second block, it invalidates the subsequent blocks because okay. Remember, this one is still valid.
Yes.
Yeah, but all subsequent blocks
are invalid.
Are immediately invalidated. Okay. And I'll be able to tell that immediately.
Okay.
Okay. Any questions up to there?
No, I understand it. I'd be keen to see. Okay, in real life, how do I apply this? Because the beauty about it is that it's immutable.
It's immutable in the sense that if you try and mutate it, it's immediately verifiable.
Exactly.
Yeah.
Okay.
So what I've done is I've come up with some sample transactions.
Okay.
We're only going to use 3 blocks.
Okay.
So I have a list of transactions in my first block, okay. In my second block, in my third block.
Okay.
And so now we're getting into cryptocurrencies. We're getting into Bitcoin, because okay. this is actually what the Bitcoin blockchain contains. The Bitcoin blockchain contains Bitcoin transactions.
Okay.
Yeah.
Okay.
So, imagine the world of Bitcoin, the people buying and selling. These transactions are being recorded in a block.
Yes.
And then you have miners. The Bitcoin software is distributed among thousands of computers. They compile these blocks together.
Yes.
Every block is the same. I mean, across the network, when they agree on the contents of the block.
Yes.
And then you have what's called the mining. So the mining now is when the computers, the miners, try and find the nonce, which when hashed together with the list of transactions and the previous hash will give us a valid block.
Okay. Okay.
So let me start my computer mining.
Yeah.
And if you're here, you could actually hear my processors spin up. The computer starts doing some work and ends up with this nonce 44507.
Okay.
This in Bitcoin terms or blockchain terms is now a valid block.
Okay. Charles, I've just observed that we've reached sort of the limit of our first conversation around blockchain, and so what I'm going to do is I'm going to pause it here,
Okay.
Because it seems as if you're now basically giving us where the blockchain and the Bitcoin come together.
Yes.
So I'm going to pause this interview
Okay.
and then come straight back so that you can now tell us about cryptocurrencies and how blockchain is how it is used in transactions around cryptocurrencies and how this blockchain technology can be used in other ways.
Okay.
Great.
Sounds good.
Thank you very much. For this and other Elephant conversations, follow The Elephant on Facebook, Instagram, and on Twitter at The Elephant. Remember to like, share, and subscribe to The Elephant, also on our YouTube channel by clicking on the link below.